presented by Amelia Henry. She's a drought physiologist with the International Rice Research Institute in the Philippines.
I'm going to be talking about our work characterizing sites used for screening rain-fed lowland rice. And for those of you not familiar with rain-fed lowland rice, it's a system where the soil is plowed when it is saturated, which is called puddling. So that is thought to create a hard pan that helps with retention of water. But in this region where we're working, in Bangladesh, India, and Nepal, what typically happens is that the field starts out as a typical rice paddy with flooding, but then it progressively dries over the season due to lack of rainfall. So these are the sites where we are working. This is our drought breeding network. IRRI is developing drought breeding lines, and we send them to these sites for evaluation in these different environments. You can see on this map, there are the red triangles are the research station sites where we have observational yield trials and advanced yield trials being conducted, and the blue squares are the on-farm sites where participatory varietal selection is being conducted. And in fact, this network has been very active for decades, but all during this time, we weren't doing any kind of environmental characterization. Each research station was growing both well-watered and drought-stress experiments, but the only distinction between those two experiments was the title. We didn't have any kind of quantification of how severe the drought was, or different aspects about the drought characteristics. So we wanted to start getting some more information about the types of drought in this environment. And so we conducted a series of measurements at each site, and we wanted to compare it to the percent yield reduction by drought. So again, each site had both the well-watered and drought-stress treatment, so we did a relative comparison of yield reduction by drought, and that was a way of normalizing for all the other factors that were maybe reducing yield at these sites in addition to drought. And we wanted to characterize the drought progression over time, so we were looking at rainfall, tensiometer readings, water table depth, and also soil physical and chemical properties. So this was a way of characterizing what was happening in our breeding trials, but it's also a way of getting a better understanding of what's going on in the real world in rain-fed lowland rice. We wanted to know what are the environmental characteristics that are most affecting rain-fed lowland rice yield under drought. And in fact, there has been a lot of quantitative work on this done in Southeast Asia, where it was concluded that the presence of a hard pan that impedes root growth, low nutrient availability, topography and clay content, both of which affect water availability, were the main factors affecting yield reduction by drought in rain-fed lowland rice. But our sites are in a different area. Most of them fall into these areas: barren tract of Bangladesh, Indo-Gangetic Plain of India, and the Terai of Nepal. So in our case, our hypotheses were that the factors that would be most affecting yield under drought were the presence of the hard pan and soil clay content. So one of the first things we started doing was to get more detailed information about the drought progression. We distributed tensiometers to all of our partners for use at the research stations. They're also using water table tubes. But this was by far the most challenging part of this project, because you can imagine if you're a breeder in a remote location all by yourself and you've never done soil moisture measurements, using a tensiometer is not easy. But after a few years of practicing, we were able to get 3 years of data from most sites that we could use for a combined analysis. In terms of the soil analysis, as you would imagine, we had a big range of different soil types in terms of soil texture. Also, the soil fertility levels, we had a big range in soil available phosphorus, but most of the sites wouldn't really be characterized as low phosphorus. We also did water retention curves. This was done at the ICRRI Soil Physics Lab. And we measured bulk density at 2 different depths. The bulk density was quite high across sites, and we were surprised about that. So we even redid all of these measurements in multiple years. The most surprising result we saw was from our penetrometer readings. So again, since rain-fed lowland rice is puddled, we expect a hard pan at about a depth of 30 centimeters. And that's what we saw in the sites of Nepal. Here you can see Hardinath, Nepalganj, Tarahara. They all have some kind of detectable hard pan. But in a lot of sites, particularly our most reliable drought-stressed sites, Hazaribagh and Raipur, we didn't detect a hard pan at all with the penetrometer. And this was using the same penetrometer at all the sites. We visited all of them at about mid-grain filling stage. So that was really a surprising result. We expected to see a lot more distinct hard pans across sites. We also compared nearby farms to the research station soil, and the only significant differences we saw were in terms of potassium, bulk density at depth, and also the maximum penetrometer reading and the depth of the maximum penetrometer reading. So that's something we want to take into account when we think about the applicability of our results from the research stations. So we put all of our data from research stations together, and we looked for what are the factors most related to the percent yield reduction by drought. And interestingly, so we ran a principal component analysis and also stepwise multiple regression. And in both analyses, this depth of the maximum penetrometer reading came out as being related to yield reduction by drought. Not the presence of a hard pan, but actually the absence of the hard pan. And we didn't see a relationship with either clay content or sand content. Actually, silt appeared to be negatively related to yield reduction by drought. So we started thinking, what was it about? How could we explain this absence of the hard pan? It seems to be so important in this region. And we realized that there was one characteristic we didn't quantify, but it's quite apparent, and that is soil cracking. So this is an image of soil in Nepal where we have the most distinct hard pans, and under severe drought, the cracks are not getting very big. In contrast, this is in Hazaribagh in Jharkhand. You can see the soil cracks are so big, the roots are getting torn. You could really get your foot stuck in these cracks. And we think that because this regular cracking is occurring, it really disrupts the hard pan. Even though these soils are being puddled every year for decades, if they're getting regularly cracked, it's disrupting the hard pan. So in summary, we hypothesized that the presence of a hard pan and clay content would be the factors that were most affecting yield reduction by drought in this region, and we were wrong. So my conclusion is that target environment characterization is still needed. And my message for scientists that are here from regional centers, if you're conducting breeding trials, especially in remote locations, if you do more detailed environmental characterization, it's really informative. And especially now, there's a lot of upscaling going on, developing global estimates using remote sensing. But all of these remote sensing techniques are depending on the ground measurements. They're making assumptions. So I encourage you to do environmental characterization. It will help make your data more scalable. So finally, I'd just like to thank all of our partners, the breeders that are working all over India, Bangladesh, Nepal, and the rain-fed lowland sites, also the ICRISAT and Modipuram soil analysis labs, and the Bill and Melinda Gates Foundation. Thank you very much.